First day is our first speaker, Dr. Jigisha Parikh, madam. Just short biodata, madam. Dr. Jigisha Parikh, madam. Madam holds a PhD from SVNIT Surat and has made significant contribution to academia and research. She has served in various prestigious roles, including former Associate Dean, Research and Consultancy, and Member Secretary at the Center for Industrial Consultancy and Sponsor Research. She also held the position of Scientist G grade at SERB, DST Government of India, New Delhi, and formerly lead the Chemical Engineering Department at SVNIT 2014 to 16. Dr. Jigisha Parikh, madam, research has been widely recognized in international journal with over 100 plus published research articles, 4 book chapters, and 2 patents to her credit. She has an impressive track record in the thesis and dissertation supervision, having supervised 10 PhD scholars with 10 more in progress, 20 students with one ongoing, and 5 MTech by research candidate. With her vast expertise and distinguished career, we are honored to have Dr. Jigisha Parikh, madam, with us today. Please join me in welcoming her. Madam.
Yeah. Thank you, Dr. Chandrapal. Yeah. Can you hear me? Yeah. So thank you once again, the coordinators of this ATAL FDP, for inviting me for this session. And the kind introduction provided. So I see that a very good number of participants are there, and I hope that they will get something out of the various presentations. So now I will start my presentation. I share my presentation and just confirm that it is so can you see the presentation?
Yes, ma'am.
Yes, ma'am.
Okay, good. And now I'm making it a full screen. Is it visible? Full screen, is it visible?
Yes,
now it's visible.
Yeah. So herewith I have been given this task to speak on this biomaterials from food processing waste, a sustainable valorization. So I will start with the concepts of this sustainable valorization, how it has been emerged. A few points with reference to how this concept has gone far, with reference to the food processing waste. Then some applications, processes will be discussed, and then I will discuss some of the research work in line with this particular topic to show you that how it has been processed, and then few challenges and solutions along with the future prospects will be shared, and then we will then summarize the topic. So this is about the presentation. About me already, Dr. Chandrapal has said few words. So presently I am a professor at SVNIT Surat. I am also Dean of Research and Consultancy, and about 30 years plus experience I am having. About 120 plus research papers, 25 about PhD students, 25 master students. Also worked as scientist G at Department of Science and Technology, New Delhi on deputation. And some explore some experience with the industries. So in combination, academics, research, industry, and the funds management and new schemes development. this kind of experience I'm having. So with this, I start with the topic. So when we say sustainable valorization, how this has come into the picture. So for around a century and a half, fossil resources were the indisputable feedstock to produce fuels, chemicals, and materials. However, the government has started paying attention to the adverse impact of climate change and greenhouse gas emissions, along with the economic crisis uh, along with the environmental protection and economic growth. So, sustainable development has become a priority for policymakers, stakeholders around the world, and with necessity to gradually shift away from fossil resources as a key endeavor. So, in line with this, all UN member states adopted the 2030 Agenda in 2015 to be involved in sustainable development. So, number of times we might have heard about sustainable development as well as sustainability. There is a small difference between these two. That's why I have put up the definition over here. That sustainable development is defined as the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Meanwhile, the sustainability concept, which is a paradigm or ideal state where social, economic, and environmental considerations balance perfectly to pursue an improved quality of life. So, more or less, both goes hand in hand. Some typical difference is there. This is actually came into the picture to encourage the use of renewable resources as the base to build a more sustainable production and consumption scheme. And in line with that, various sustainable development goals has been introduced by UN. Okay, so few other definitions with reference to that the bioeconomy concept came into the picture, which is based on the need to overcome the damage caused by non-renewable resources. According to the Food and Agriculture Organization of the United Nations and the European Commission, the bioeconomy is based on producing renewable biological resources and converting these resources and waste streams into value added products such as food, feed, bio based products, and bioenergy. At the same time, the German government defines the bioeconomy as a sustainable bio-based economy oriented on the natural life cycle of materials, which can provide us with high quality products from natural resources and sufficient healthy food to satisfy the global demand. Similarly, the National Bioeconomy Blueprint says that a bioeconomy is based on research and innovation in the biological sciences to create economic activity and public benefit. The US bioeconomy is all around us: new drugs and diagnostics for improved human health, higher yielding food crops, emerging biofuels to reduce dependency on oil, and bio based chemical intermediates, to name just a few. And finally, the Organization for Economic Cooperation and Development, OECD, defined bioeconomy as a world where biotechnology contributes to a significant share of the economic input. So, more or less, if you see that it covers that we have to replace the non renewable resources and we have to optimize the outcome in terms of bio based chemicals, products, okay, and to reduce the waste along with it. So, in line with that, biorefinery concept came because today's topic we are talking about food processing waste or food waste. All are with reference to the bio-based components. Okay, so that's why biorefinery concept is equally important. So, according to the International Energy Agency, Bioenergy Task 42, a biorefinery is defined as a sustainable processing of biomass into a spectrum of marketable products and energy. There are various definitions, but this is the one we normally consider. And another one, along with it, is a network of facilities that integrates biomass conversion processes and equipment to produce biofuels, energy, and chemicals from biomass. So, this biomass is nothing but the waste, biological waste, bio waste basically, which we are considering for today's topic. So, after that, according to the United Nations and Sustainable Development Goals, food waste management is highly recommended for the attainment of Sustainable Development Goal number 2, that is zero hunger. Number 7, which is affordable and clean energy, and number 12, responsible consumption and production. So far we are working on a linear economy wherein the concept was take, make, and waste. However, if we want to attain these sustainable development goals, we have to move toward reduce, reuse, and recycle, that is, make, use, and return, which is now as coined as a circular economy. So, circular economy at a larger extent, it is a very big network of various type of materials, that is waste materials. Its valorization, it's through the pretreatment, various conversion processes, okay, and then convert it into the various products, okay, like biofuels, hydrogen production, energy, and any other components which are useful. So you can see that sustainability is important part. Optimization of the process is another, various pretreatment processes, okay, conversion processes, different type of waste, okay. So all these together will make a circular economy, including this waste biorefinery. So last 10 years this has come into the practice, and along with that life cycle assessment, sustainability index, to identify whether it falls under this particular circular economy or not. Accordingly then it can be proven. Okay, so if you see here circular bioeconomy, wherein your waste at micro level, that is, at present companies are having some recycling treatments for their waste. However, at a meso level, we have to consider that industrial symbiosis with reference to that utilization of these waste resources in terms of products, in terms of services, and then it can be taken up further at a macro level. Okay, so combination of all this will give biorefinery inclusive of different processes, will give us the circular bioeconomy, which will ultimately turned up into the sustainable development. Okay, so the prime goal is to reduce environmental, societal, and economic cost, economic competitiveness enhancement, and to slacken poverty and hunger. Okay, so bioeconomy, this circular bioeconomy aims towards waste to wealth concept, which gives birth to new technologies, jobs, and livelihood, along with intrinsic benefits to the environment. Okay. So with reference to this, if we move further, now this can help us in attaining particular goals, as I said earlier. Okay, so number 1, 2, 7, 11, 12, 13, and 15 out of 17 sustainable goals can be achieved. Here we have considered the food processing waste, including the smart manufacturing and industry 4 concept with a circular economy to develop value-added products. Okay, so this is a sustainable approach which we are looking forward. So both the sustainability and bioeconomic concepts should be integrated, which is now known as the sustainable bioeconomic concept, which involves sustainability metrics related to the economic, social, and environmental performance of those activities considered in the bioeconomic framework. So it has been divided into three aspects, wherein we have to use the renewable biomass and we have to develop efficient bioprocesses to achieve sustainable production. Second aspect is focusing on the use of enabling and converging technologies, including biotechnology. And the third aspect is the integration. This is very, very important if we want to establish this circular bioeconomy between various sectors, because we can have multi feedstock biorefinery applications in various health and other industrial productions. Okay, because at number of points, see, earlier it has been started with that replacement of petrochemical refinery with the biorefinery, but in certain cases it has been also observed that It's not only the replacement of the petrochemical refinery, but number of products which are not possible to develop through the petrochemical routes is also possible through this biorefinery route. Okay. So here just to show you that what is the bio waste boundary. There are waste, various waste like paper industry, food industry, animal food processing, municipal solid waste, and so more. Okay, so wherever any carbon based material is there, or other than the carbon based materials which are useful materials which can be extracted or converted to produce a value added product, are considered as bio waste. And then we have to treat it accordingly to go further with various processes to develop a typical type of product which is useful for, once again, a typical application. So there is a lot more to consider under these particular processes, whether it is a biological conversion, thermochemical conversion, or any advanced and hybrid conversion techniques. So technology boundary also one has to identify depending upon which type of waste is to be utilized, which type of product is to be produced, and for which particular application it is to be utilized. So here further product slate has been uh, mentioned over here, particularly with reference to the food waste. So if you can see that under food waste, even animal, poultry derived waste also considered, industrial food waste where dairy, vegetable processing, cereals, food processing waste also come, even plant derived because tubers and sugar crops also fall under the food grade products. Okay, so you can see that a very big slate of products is available which can be derived through various processes from this waste. So, if we combine all these concepts together, you can see that we can develop this concept of circular bioeconomy through this recycle, make, use, reuse, and remake, wherein all the environmental impacts, societal impacts, and economic aspects are covered together. So, our aim is to establish or to work towards this circular bioeconomy. So, if we come to our today's topic with reference to the biomaterials production from the food processing waste. So, food processing waste is with reference to food waste as well as industrial food processing, uh, different food processing industries. Okay, or waste generation through those different processing industries. So, globally, if we see in million tons, European Union are the largest producers of this food waste, about 88 tons, followed by India, USA, UK, Malaysia, Japan, and Australia. And share of these various global food waste in terms of typical type of products. So fish and seafood is 1%, oil seeds and pulses 3%, meat 5%, milk and eggs 9%, root and tubers 19%, cereal 24%, and if you see the largest share is for the fruit and vegetables. Now all these contain various different type of components like starting with the carbohydrates which are nothing but the cellulose, hemicellulose, and some proteins along with lignin, pectin, lipids, and number of antioxidants and major nutrients which are present in these components. Before we move to the different processes, the important consideration with reference to the carbon footprint we have to consider. So, in terms of the food, 50% we consume. Okay, so that is the food eaten. However, 50% is due to the losses of supply chain or food thrown by retailers or food this lost during the production, that is waste generation during the production stage. So, if you see that 50% of it is going into the this carbon footprint, so we are losing lot of carbon or generating very good amount of or very high amount of carbon emissions. Okay, so if we utilize this particular 50 percentage, we can reduce this carbon footprint on our earth. So if we see this food waste valorization in terms of circular bioeconomy, we have to identify that where we are losing and how we are losing. Okay, and how we can tap these resources under various processes. Okay, so if actually it is a fresh food, then we can make use of it for animal feed, or we can reuse after some time. Okay, because this is all edible, this green is given as an edible path. Okay, so wherever possible, we first try to get it in terms of edible so that we can make it utilized. However, this particular paths are shown as the inedible because this is now not useful for our feed. Okay, so then it is to be collected, sorted out, and then can be utilized through various processes. So one has to identify this kind of network for whatever type of food waste they are considering. Okay, until what they are recovering either as a nutrients or as an energy or as a different type of products. So this kind of network development is very very important to establish the circular bioeconomy. So here one more type of that. So food waste from these different four sources has been considered. Okay, so here if you see, these are the new techniques which are employed under this concept of circular bioeconomy to develop bioactive compounds like pectin, polyphenols or carotenoids, bioplastics, then biofuels. Okay, either you produce all three or you produce as per the process configuration, which one is the most valuable. So here, if we want to go for circular bioeconomy, various researchers have proposed certain network. So one of the concept is that integrated biorefinery model for the conversion of this food waste into value-added products. So you start with the generation of that food manufacturing, food packaging, even if it is a home kitchen or whether it is a food bin. So task of sorting and isolating of waste is very very important, and then you sort it in terms of what is the common component of those particular materials. So it will be easier to identify the pre-treatment and then the secondary treatment procedure to develop a typical type of materials or to extract the typical type of materials, and then you can go for the um, specific conversion processes which will give you the different products like biopolymers or biochemicals, enzymes and protein productions, or even biofuels. Okay, so once you identify this particular type, okay, you further go to this, what you are getting, what kind of potential it is having. According to this, you sort this out, identify the pre-treatment process, identify the secondary process. At the first stage, you may extract some of the important material, and in the second stage, you can develop or you can have a conversion process which gives you a typical type of output. Okay, and then whatever waste is still remaining with you can be utilized somewhere as a biofertilizer because it is a biological waste. So it can be further utilized as a biofertilizer also, which will be then useful for the generation of plants for foods. And here, through the use of solar energy once again. So this particular cycle completes, and that's why this concept we are considering as an integrated biorefinery model. Okay, so this involves a combination of various waste treatment and conversion processes to maximize the value extracted from waste streams like this food waste. This integrated approach aims to enhance resource efficiency, reduce waste, and support the sustainability. So these integrated strategies are being investigated in order to further improve the economics of food waste treatment, increase product yields, and lower existing high manufacturing costs. So these are the typical technologies normally employed for any waste treatment technologies. So thermochemical conversion, which are further classified as pyrolysis, gasification, liquefaction, incineration. So all these are leading to the bioenergy products. Biochemical conversion, different other products, composting, fertilizer, anaerobic digestion. Once again, it can be utilized as a natural gas generation, and the fertilizer Landfilling is not a good option for the circular bioeconomy concept, and fermentation to produce the ethanol, butanol, and other components. Similarly, advanced techniques for the extraction of the components before we go for these particular technologies. Okay, similarly, emerging technologies are also coming up for number of such conversion processes. So, what kind of biomaterials are being produced from the food waste? So, it is known as a food waste biorefinery. Okay, so you can have a biofuels, biofertilizers, carbon-based materials, solvents and valued chemicals, silica and silicates, biopolymeric materials, biosurfactants, flavonoids, phenols, alkaloids, bioplastics, to name a few. Where these materials are being utilized, I will show you two typical different type of applications. So here, if you consider biopolymers, then its application in pharmaceuticals, in drug delivery systems, a lot of bio-based materials, biopolymers are being utilized. Even for the manufacturing of these implants, now biodegradable implants are being coming up. Wound healing requires lot of materials, out of which some of the biopolymers can be utilized. We are also working in one of the project for this wound healing. Even diagnostic tools can be developed for the utilization by the utilization of these biopolymers. Gene delivery, stabilization of proteins, tissue engineering, vaccine development, these are some other areas wherein biopolymers developed out of this concept can be utilized for the pharmaceutical industries. Similarly, another one is the food technology, where a lot of such biopolymers are being utilized as an edible films and coatings. One case study we will be discussing for this: food packaging, thickening and gelling agents, encapsulation of flavors and nutrients. We are working on two projects on this particular type of work. Then fat replacers, stabilizers in dairy products, nutraceuticals and functional foods, biodegradable cutlery and tableware, to name a few. So these are the further applications of those biomaterials which are being developed from the food processing waste. And for that matter, even biomass, different type of biomasses. So here one such integration for the dairy waste is shown for your reference. So dairy industry waste, particularly waste are there. Okay, so these are the various processes through which this milk waste is generated. Then it is further hydrolyzed and fermented for the transformation of this milk waste to a typical EPS synthesis from this milk waste. And then it is being EPS, which contains alpha D glucan, beta D glucan, and beta D fructan as its composition. Okay, where the application is, it is particularly useful in healthcare sector to promote the intestinal health, alter microbes composition, enhances immune activity, and improves the blood flow. Similarly, microbial conversion of this milk waste into different products is also possible, wherein you can produce the glycerol, ethanol, or biomass as a feed for fish or animal as a value-added products. Applications obviously: alcoholic beverages, hand sanitizers, medical wipes, various solvents, and fuel. Okay, so you identify a typical waste and then you identify the processes based on your application. Similarly, vegetable waste utilization, same, you identify what typical type of waste you want to consider, which is applicable for a typical type of product development. Okay, so here if you see, pre-treatment is required to loosen the components because it's a hard polymers. Here, enzymatic hydrolysis is employed to develop this typical lactic acid, propionic acid, or butyric acid. Okay, and this founds the application in terms of the sustainable fuel or utilize nutritive resources for animal and human to mitigate the byproducts. Okay, so these are various such processes which can be considered. Even here, you can see that we can have these carotenoids or microbial lipids or this glycan for the food industry itself. So once again, it completes the cycle: food waste generated, which can be utilized for the production of the bio components, which further are utilized for the food industry itself. Okay, so completely integrated approach. So one case study from the literature I am putting up over here for your reference. So here it is a potato peel waste valorization technology, which is shown in different color boxes. So first, this potato peel waste extraction has been employed, different type of extraction. Okay, and phenolic acids possessing antioxidant properties are being extracted from the waste feedstock. So this is the first step. Okay, so uh, waste collection, sorting out, preparation, feed preparation and all, and then the extraction technique along with an novel extraction technique with a typical type of solvent. Okay, so phenolic acids have been extracted. Now, once this is done, you have a liquid and solid materials available. So further that solids which are remaining are, that is carbohydrates. These are being hydrolyzed and dehydrated to yield a key platform chemical which is known as hydroxymethyl methyl fulfuran. Okay, so that is being produced from the uh, second conversion process, and then this HMF is being separated through different unit operations from the organic solvent. And finally, the third component which is remaining, that is the lignin, it is separated and it is then pyrolyzed to manufacture the biochar, which can be further utilized either as a source of energy or as a adsorbent or as a uh, composite preparation. Okay, so a lot of different applications are there, but here if you see that starting from the waste material, that is potato peel waste, okay, it has been utilized. So immediately those extractives has been cleared out, then remaining carbohydrates are converted to a different chemical, that is biochemical, which is very uh, rich source of the fuel additives and different other chemicals. And then left out lignin material was utilized as a biochar. So once again, complete integrated approach. Okay, so in terms of the figures, if you see over here, so these are the mechanisms which are shown over here for the formation of these various products out of this potato peel waste. And if you see over here, these antioxidants are about 240 kg produced. HMF is produced about 130 kg and biochar produces about 50 kg. Okay, so this here it has been shown in terms of this ethanol lignocellulose, then this 1, 2, and 3. So PPW1 assumes that HMF is the only product, whereas number 2 considers HMF and biochar as the product, and number 3 is the production of extractives, because lot of extractives, different nutrients are present in the peel waste, potato peel waste, which are also recovered. Okay, so this is the best production utilization of this potato peel waste through the extraction of these antioxidants, then conversion further of carbohydrates into the hydroxymethyl furfural, and then conversion of the lignin into biochar. Now, some work from some of my students, particularly because we were talking about the extraction. So, one point I wanted to share with you, that extraction of this from different type of grasses, citronella oil and other extractive oils are being produced from these sources of different type of grasses. Okay, so here the main point or main concept is to identify a novel extraction technique which is useful in terms of this utility consumption, in terms of yield, in terms of total phenolic content, less power consumption and less carbon emission. So few five different type of methods has been employed for the extraction and then compared. And if you can see over here, the comparison is given with reference to how much time is required, what solid loading is there, what solvent volume is required, and what is the power consumption. Okay, so these four parameters have been identified through the optimization to compare these extraction techniques. With reference to this, you can see the responses that uh, through this HD This is a conventional process 1.89, whereas all the other novel techniques, if you can see that it is higher than what is available in the conventional technique. And IHD, that improved hydrodistillation method, has given us the base yield 3.19, along with, yes, other components which we have to consider. So here if you compare the utility requirement for all these and energy consumption along with the carbon emission technique, so from this we can optimize that under which condition which particular technique we have to employ upon. So now if we consider only the extraction from that particular material, we cannot consider this under biorefinery concept. Why so? Because this is, you can see over here, the yield is only 2%, around 2 to 3%. That means something more than 90% is the waste which is being generated from this. So what to do with this waste? So we have to go for that integrated approach. Okay. And we have to, once we extract this essential oil and phenolics, we have to utilize that solid waste which is available. So either we can fractionate it in different components, and then we can go ahead with the processes to develop the biochemicals and biopolymers. Okay. Herein, what we have done to achieve this zero waste condition, that we have developed the biofuel out of that material, which can then we have developed the biochar for the adsorbent, and we have also developed the composites which can be utilized for certain applications. So this is how we have employed this zero waste concept over here as an integrated approach for this particular extraction material and this various type of grass. Now, with reference to the biomaterials, one research study wherein we have synthesized the nanocellulose. So here, what we have considered, that our aim is to synthesize nanocellulose, and the components which we have considered, that is food waste or food processing waste, which we have considered are the sugarcane bagasse and pineapple crown leaves. Okay. And here we have employed, of course, along with the conventional techniques, the novel technique which we have employed is the utilization of deep eutectic solvents along with the ultrasonication technique. Okay, so this is a combination of the technique. Now here it can be a one-step process or two-step process depending upon the type of the material. Okay, so this procedure consists of treating the biomass with typical DES, which is choline chloride with glycerol in the first stage, and followed by further treatment with another type of DES having choline chloride with oxalic acid. And later the resulting mixture was rinsed and dried to obtain pure form of cellulose, which was then in the second step was pre-treated for the development, and the supernatant was then processed with the ultrasonication technique to obtain the nanocellulose. Okay, so what are the research gaps and challenges in this particular study? So here the variability in raw materials, because it is heterogeneous in nature. Okay, components are differing because all are having different type of extractives and different amount of cellulose, hemicellulose and lignin, and of course the inert material into it. Efficiency of the process, of course, we have to increase upon environmental impact in terms of the this life cycle assessment, and sustainability index has to be calculated. We also have to look into the residual impurities, because these are the waste materials. So what impurities it carries along with it? What is the energy consumption as a whole or individually under the particular process? Functionalization, because each material cannot be functionalized. So we have to identify that what type of functionalization material itself is carrying, or if we want to produce another product, whether some functionalization is possible or not. Stability of the material in terms of the product. Okay, so product whatever we produce, whether it is stable, is durable for a longer time to be utilized for a typical type of application. Challenges is the optimization, that how do we optimize between various parameters. We have to identify the impact of various parameters. We have to identify the pre and post processing methods for a typical type of application, because the moment the application is changing, your selection of the pre-treatment and processing treatment conversion process differs. Okay, and utilization of the green solvents. Okay, because a lot of organic solvents are being utilized for this extraction or the conversion of the materials. So if we want to go for the circular bioeconomy, we have to try to replace those solvents by the green solvents, so to reduce the environmental impact and to increase the sustainability index. Now, this nanocellulose, there are different types of nanocellulose. The major three types are placed over here for your reference. So, when we say that the cellulose nanocrystals, these are rod like crystals with widths and lengths ranging from 100 to 350 nanometer and 3 to 20 nanometer respectively. Cellulose nanofibers, they have lengths up to a few micrometers, but only their width range from 5 to 60 nanometer. And there is, sorry, there is the bacterial type of nanocellulose where um, it is produced extracellularly by microorganisms, and it measures in micrometers and sizes between 20 and 100 nanometer. There are various types of applications of this nanocellulose. So as I said, it can be utilized for conductive materials, green materials, biomaterial in biomedical sector, like we have seen in the earlier photograph, different biomedical applications. It can be utilized to produce composites and films, packaging materials, hydrogel compound. Once again, it is a, for biomedical or environmental remediation. We can produce this. Even for wood adhesives can be produced from this. Emulsions can be prepared, which can then be utilized for different other applications. We can produce the cosmetic products, ion exchange membranes, sensors, optical materials, absorptive materials. So these are the various applications where nanocellulose can be utilized as a uh, major raw material along with other typical materials. So mechanism of the formation of this nanocellulose. Okay, so as you know that cellulose is a, sorry, cellulose is composed of polymatrix chain of linear 1,4 anhydrous D-glucotyprenose according to its structural composition. The repeated building blocks of the cellulose molecules are illustrated by the anhydrous cellobiose, which is made up of two anhydrous glucose units. Each unit has three hydroxyl groups with distinct reactivities at the C2, C3, and this C6 locations, which can help in establishing intramolecular and intermolecular hydrogen bonds. Okay, you see over here all these intramolecular and intermolecular hydrogen bonds. Okay, and enable the development of three-dimensional, highly structured crystalline structure. Okay, so we have to first have a pre-treatment process required to loosen the material, because after that we require the depolymerization of the cellulose to provide us with the nanocellulose. Okay, so we have to loosen the structure. For that we have to have some water addition and hydrolysis, and then acid pre-treatment is also helpful in that kind of structure. So to break these bonds, acid pre-treatment is required, and then there is a hydronium ions uh, requirement is there for the protonation reaction. Otherwise this branch structure will not get break, and we have to break it through these ethers. Okay, so the amorphous and crystalline regions of cellulose microfibers are distributed randomly along their path. Okay, and it is very much disordered and readily once readily breaks only if house treatment is given, or cellulose chain which is densely packed, we have to loosen it, that structure, and then further depolymerize. So overall we can say that acid pretreatment uses hydronium ions to attack and break down intramolecular and intermolecular bonds in this uh, biomass hierarchy structure of hemicellulose, cellulose, and lignin to disassemble the complicated structure of this biomass resource. So here if you see that once it passes through these three typical processes, okay, now we have this independent structure. So now it has been depolymerized and converted into this nanocellulose material. Okay, so in terms of the methodology, as I said, we have used a sugarcane bagasse, okay, and this is the pineapple crown leaves, which has been further feed preparation. So we have to convert into the uniform size before we utilize it under this typical process, okay, and then uh, we receive this cellulose extracted from it, okay, depolymerize, and then the conversion of this into the this nanocellulose, because here we have used the whole biomass. Okay, so we have to extract first the cellulose, and then cellulose is converted into the nanocellulose. So here we have obtained maximum yield of about 77 percentage from the sugarcane bagasse, and in case of the this pineapple crown leaves, we have received about 69% of the nanocellulose. So as I said, because of the structural variation, the yield will be different. So you have to identify that what possible yield is can be derived from this, and accordingly, as I said, you have to apply the typical pre-treatment as well as the post-treatment method. So either you can go for the one-step process, or you can have a two-step process. So combination of various pre-treatment, multi-parameter pre-treatment also is possible. So here we have utilized, instead of the conventional process, we have utilized the TS as a green solvent along with the protonation reaction. Then the product, because we have to validate that whether we have received the product as per our requirement. So XRD was performed, okay, for the this derived nanocellulose from SCB and PCL, okay, and this is to identify the crystallinity index uh, with reference to the nanocellulose. So here it has been compared that this black refers to the biomass, that is sugarcane bagasse, and this one here you can see that with this 110 plane, that crystallinity has increased, okay. So similarly here on 200 plane, okay, because it is a three-dimensional material, so different planes have been identified, and this crystallinity index has been shown over here. Similarly, with the PCL, so here you can see that here crystallinity index has increased, and here also crystallinity index has increased. Okay, so we have received a very good crystallinity increase in crystallinity index, because this is very very important if we want to use it as a nanofiller or additives in the polymer composite. If it is not crystalline material, then it is not useful for that particular application, and hence we have to identify this index through the XRD measurement. Similarly, to identify the uh, structure variation, okay, or morphology, we have performed this scanning electron microscope, and TEM images are shown over here. So here uh, you can see that the length of this synthesized nanocellulose range from 80 to 120 nanometer. So it is the cellulose nanocrystals which we have obtained as per the first type of nanomaterial, which was our uh, identified outcome. So we established that yes, we have received that cellulose nanocrystals types of material. Okay, so that range from this particular SCM and TM images we can identify length of this. Okay, similarly, we have also performed the zeta potential for both the components. Okay, so if you see this figure, the zeta potential of this nanocellulose derived from this both component is coming to minus 25 and minus 19 millivolt. Okay, and this is important because it signifies the occurrence of negatively charged functional groups on the surface of nanocellulose. Similarly, another parameter which was identified by the atomic force microscopy, okay, which shows the 2D and 3D images of both the derived nanocelluloses. So it shows that a long fibril structure in these images has been identified. Okay, And this indicates that the chemical and mechanical treatment eliminated the cementing components, particularly hemicellulose and lignin, around the fiber, these fiber bundles. Okay, so this confirms the removal of that hemicellulose and lignin from this nanocellulose. Okay, so this validates the formation of very good quality of nanocellulose crystals. Okay, so overall, in the present work, we can say that nanocellulose or nanocrystals were successfully isolated from both the type of material, that is sugarcane bagasse and pineapple crown leaves, using deep detective solvents along with ultrasonication process. We also employed the optimization process through box bank and design to study the effect of process parameters so that we can optimize to reduce the environmental impact as well as the energy consumption. So we can say that under the current study, we have developed green and two-step optimized methodology for producing thermally stable and dispersible nanocellulose crystals. The improved crystallinity suggests that it can use as a biofiller for reinforcing polymer composites. However, there is one challenge still remains, and that is that simple, and because we are using deep detective solvent, so that has to be actually if it is an integrated biorefinery approach, we have to reuse this solvent. So we have to identify the simple and cost effective recovery of this deep detective solvent because it is a significant issue after the pretreatment. So though successful outcome, but as I said, it combines a number of processes together. So this one particular challenge is still remaining. Now we come to the second part of the biomaterials, that is it application part. So one of the important application, as I have shown earlier, is with reference to packaging. So why bio-based packaging? Why it is important? So we all know that a recycling process of plastics, especially the conventional petroleum-based plastic, is very much difficult due to the complications with various mixtures of plastic types. Okay, and their prevalent usage in almost every industry, coupled with the extremely slow degradation rate, as you know, about 10 to 10 years to or even 500 to 1000 years of conventional plastics. This has led to serious environmental problems, including the formation of meso, micro, and nanoplastic that could accumulate in all ecosystems and are also biologically hazardous to almost all trophic levels of the food chain. Okay, so there are various when earlier plastics came into the picture, it was very much absorbed by all the community, okay, because it has given us a very good output. But now it has raised so much societal concerns, okay, and with reference to that, this gives you the positive and negative aspects of food packaging throughout its life cycle. Okay, and with this basis, uh, we can say that bio-based packaging, what kind of impacts it can give. So we have, because for packaging we require tensile strength, so that is available. Thermal stability, water vapor or UV barrier properties, that is also possible. The important criteria: improved soil biodegradability, which is not available with the conventional plastics. Inhibition of bacteria, fungi, and other pathogens is also possible with this. High durability and prolonged shelf life in comparison to the plastics, so it can be replaced. Further important criteria is antioxidant activity, which is not possible with the conventional plastic. Hydrophobicity and reduced hydrophilicity, depending upon which type of material we are using for the packaging. And obviously, intelligent packaging system that can indicate freshness, which is once again not possible with the conventional plastic. So we can say that these are the certain features which put this bio-based packaging as a attractive one with the plastic packaging. So in this line, we have another work wherein we have prepared the composite films. Once again, utilized these food processing waste as a raw material. Here also, as I said, pre-treatment, post-treatment methods are being utilized. So once again, depleted solvent has been utilized to fractionate the biomass material into three different fractions of hemicellulose, lignin, and cellulose, which were then further utilized in the formation of these composite films. Okay. So cellulose here has been converted to the carboxymethyl cellulose because directly utilizing cellulose is not good. We have to have carboxymethyl cellulose. So methylation process was employed to develop this carboxymethyl cellulose, which is an anionic cellulose ether. And in packaging film applications, the viscosity of film forming solution can be adjusted by this CMC. Okay, so this helps in the adjustment of the viscosity. Also, it offers a protective barrier, and hence, instead of direct cellulose, this converted product of the cellulose, that is carboxymethyl cellulose, has been utilized, and it is an essential industrial biopolymer. Also, other application that does not have any adverse impact on human health, and it is an efficient polymer for improving the product quality, and hence CMC has been utilized over here. So different four films were synthesized. So CMC is the common in all. Then CMC plus hemicellulose has been utilized to form the film. Then lignin and hemicellulose. Uh, then the CMC and lignin, and CMC hemicellulose and lignin. So these four components utilized in a different way to produce the four films out of the waste material. Okay, so here the FTIR results for the fractionated material. So this is the cellulose. Okay, this is confirmed by these FTIR methods through these bonds. Then this is the methylation product of the cellulose, that is the carboxymethyl cellulose. Okay, then this is the hemicellulose which has been fractionated, and this is the lignin material which has been isolated. Okay, so we have received the pure material from the fractionation, and then those materials were utilized in the formation of the films. Okay, so these are few features of the film with reference to the component. So thickness uh, ranging from zero point 0.1 to 3, or rather we can say that 0.068 to up to 0.176. Contact angle is received. This contact angle, this is with reference to identify whether it is hydrophilic or hydrophobic. Okay, so if hydrophobic is there, then we can utilize this for the uh, food packaging where moisture is not required. Okay, similarly, tensile strength has also been, because durability of the film is very very important. It should not crack or fracture away or torn away. So minimum tensile strength is required. So that has also been measured from those films. If we compare these four films together, film 2 displays the highest tensile strength of 9 MPa. So this is because film 2 contains the lignin, which possesses the ability to improve its compatibility with the polymer matrix. Okay, because it is a very typical type of polymer, and thereby improving the mechanical properties. Okay, so here one is the comparison, and another one is the utilization of this different film for different applications. Okay, depending upon the characteristics which we receive out of these films. So here TGA also has been performed. So this gives us the uh, thermal stability of the films, that up to what temperature it will be uh, it will not degrade. Okay, so that has been identified for all the films. Okay, so initial moisture removal is there, and then up to this particular temperature there is no degradation, and then there is a degradation, and then here this provides the comparison between all those films. Similarly, tensile strength has been measured for all these films, and if you see that in earlier I told film 2, that is the major lignin part, so possesses a very high tensile strength. So wherever that type of durability is required, we can utilize that film 2. Okay, similarly, sorry, 1 minute. We have performed the water absorption test of the films and the UV barrier films property. This water absorption, why it is very very important, because it plays a crucial role in finding their suitability for packaging purposes. So here if we see the film 4 has shown a very good water absorption capacity of nearly 65% and also a higher contact angle of 99.9, which has been shown earlier. Film 4 so we can say that it is a potential candidate to be used as biodegradable film or in coating applications due to high water absorption capacity. So in terms of UV properties of films, if you see film 3, number 3, this blue one, this shows the highest UV barrier properties. The presence of lignin significantly impacted the property of this film. Therefore, this film 3 can be utilized to protect food products rich in triglycerides such as liver or fish oil from the harmful effects of sunlight. So, in number of products, we might have seen that keep away from the sunlight. That kind of suggestion is given on the label. Okay, so this is one kind of that characteristic which requires on the packaging, that it helps the material or the product uh, from the harmful effects of sunlight if they contain these UV properties, UV barrier properties. So overall, in this study, hemicellulose, cellulose, and lignin were successfully isolated from lemongrass leaves with conventional alkali and DS pretreatment. All the composite films were successfully synthesized and methodology was optimized also. The average thickness was in the range of 0.06 to 0.15 mm. FTA results showed the cellulose was successfully converted to CMC via the carboxymethylation process, and the components were successfully bonded in the films. All the films are relatively hydrophobic and with superior contact angle, particularly film 4 with 99.9 degree of the contact angle. A synthesized film depicted good light transmittance, which is useful for UV barrier properties. Tensile strength value of 9 MPa was observed with film 2 among all composite films. And as we have seen, all the synthesized films have different properties, so we can identify those properties with a typical application. So films fabricated by this method can become an attractive choice for the application of packaging materials. Okay, so now let us see the challenges and the possible solutions and future prospects. Here, I consider, because we have talked about this bio-based packaging, so we are discussing those keeping in the center. But similarly, either with reference to the application, with reference to the process, or with reference to the type of waste, we can identify, or along with all the three as an integrated approach, we can identify the challenges, solutions, and future prospects. Okay, so high production cost, that is the one of the major challenge at present in bio-based packaging in particular, but in general for integrated biorefinery products also. So what we can do, that research and development to optimize processes, exploring cost-effective production technologies, and some financial support for this research and development, obviously. What are the prospects? Development and implementation of more efficient production technology, availability of financial incentives and subsidies for bio-based packaging, and establishment of economically viable business models. Okay. Another challenge is the lower performance characteristics compared to conventional materials. So, when we have seen the characteristic features of bio-based packaging, some are good or new with reference to the plastic, but some are still has to be established. Okay, so innovation in material science. Okay, to improve the quality of the materials, modification of existing materials to enhance the performance, and we have to develop accordingly the processes, efficiency of the processes, and we have to identify that how a particular quality can be enhanced for a typical type of application. If that can be done, then we can remove this particular challenge. Legislative ambiguity, a lot of policies and clear, comprehensive, and supportive regulations are required for the production of this material. Widespread adoption of industry standards and increased collaboration between industries. So earlier we talked about this integration in terms of the various sectors. So if that is done, then it will help in, because suppose an industry is producing food waste, and if they handle with the other company who wants to utilize their waste for the generation of the new materials, then that hand holding, that collaboration between industries will be very very helpful. Similarly, laws and policy makers can come into the picture for support of the development of these kind of industries. Another important one is the lack of consumer awareness and acceptance. So that has to be, of course, campaigns are to be launched so that consumer awareness can be raised, demonstrating the safety and performance of these bio-based materials through rigorous testing and certification. And that's why, if you have seen, we have to validate the characteristics of the material which we are producing. Okay, because customer should convince that yes, if I use this particular material, I won't find any problem, and it is really possible to replace the conventional material. Then the technological constraints in waste treatment and conversion. So advancements are of course necessary through this promotion of research and innovation in this particular area. And overall, in terms of the bio-waste valorization, life cycle assessment is a very very important criteria. So techno-economical aspects, then socio-economic aspects, environmental aspects, and yes, safety aspects in terms of the biodegradability and toxicity is to be considered if we want to establish this circular bioeconomy. So challenges in overall terms, what we can say, because when we perform the research, we think that a lot of work we have done, but a number of stages we have to cross check. So reproducibility, whether it is possible to reproduce the material with the conditions which we have established, because if it is not, then it is of no use on the larger scale. Similarly, scalability. At a laboratory scale, we produce 1 gram or some very small amount of material. So, what are the issues which we will face if we increase the production in terms of? So, we have to establish the bench scale, pilot scale establishment, and then only we can establish the industrial or commercial process. Okay, at the same time, we have to see that whether we have enough marketability, whether we will be able to sell this particular product, or we can replace it with the conventional materials. So we have to perform the technical and economical feasibility with reference to the various challenges and issues. Along with that, as I said about life cycle analysis, so environmental viability through those various index. And then only if all these are established, then we can have a very good sustainability index, and we can establish the complete bio-waste valorization for the for our requirement. So normally a SWOT analysis is being performed. It can be either with a multiple various type of resources of bio waste or processes. Okay, so whatever you want to consider in terms of this integration, you have to identify that what are the strengths. So if we consider a few points under the strengths, that there is a possibility to turn these waste streams into valuable resources. Okay, there is a possibility to generate jobs, economics improvement. Okay, and many technologies have been developed so far. Okay, and great potential as such has been established. However, lot of weaknesses So what are the weaknesses to establish an industrially or commercial process? So commercial demonstration is still lagging behind because of very high cost of this new material development in terms of processing, in terms of characteristics establishment. Financial constraints are there, okay, and the demand supply gap is very high in terms of the conventional materials. So we cannot establish the sustainability because of this particular weakness, okay. Similarly, we have a lot of logistical, technical, economical and environmental factors, and seasonality, because continuous availability of the raw material is also a constraint. So then transportation, whether we should go for the centralized approach or decentralized approach, because we have to collect this material and it is very bulky and low value material, okay, and density is very low, okay. So transportation cost is very very high. Along with that, the characteristics very heterogeneous and diffuse. So processing of these materials becomes expensive, so putting it at a cost disadvantage. So similarly, we can identify the opportunities and threats. So once this is done, one by one, we can improve upon the challenges by improving the processes, transportation, decentralized approach or centralized approach, depending upon what is the uh, area in which it is available. Okay, so number of factors, so complete detailed analysis is required for this establishment of advantageous sustainable bioeconomy per se. So now I will summarize that exploitation of these waste organic residues, that is in this case food processing waste or food waste or any other biomass, would obviously enhance biorefinery competitiveness and social acceptance. Okay, the entire process should be evaluated as an integrated strategy, and a proper cost benefit analysis of the approach is required. Uh, as I said, generation of waste residues, if it is in excess, is could lead to a supply of any important feedstock. But at the same time, we have to see that consistent supply. So, uh, this centralized approach or decentralized approach, which we have to consider, we have to see. Regulations and directives may be established to facilitate the transition from a linear to circular economy, which will be enabled through the exploitation of available waste resources. At the same time, novel technologies are being developed to optimize exploitation of waste and byproduct streams via sustainable approaches. The establishment of integrated biorefineries, this will lead to the development of innovative bio-based industries, open new market opportunities for bio-based products, and achieve efficient resource utilization. So a way forward is we have to reconfigure the current mindset to make the closed loop approach a social norm, which will help to transition from the petroleum refinery to waste biorefinery, and at the same time comprehensively addressing the sustainable development goals. Fully exploiting these bioprocess capabilities may translate them into technological models in the near future and provide a draw of bio-based products, ideally restoring the natural pristine environment towards a zero waste earth. So overall, important criteria is the combination of this waste management, biorefinery and sustainability. So uh, we have to accept this, the we have to consider in the current market the composition and availability of feedstock, quantities required to meet the market demand, effectiveness of resource recovery, as well as the techno-economic viability and sustainability, which are the primary challenges uh, we are facing currently. So, the development and utilization of process models that forecast the outcome in terms of economic value of the process being evaluated, this will assist in the steering investors, policymakers toward the direction of spending more money on this various development for the biorefinery plants. Another major flaw which we have seen in terms of the models, that is integrated biorefinery models. So we have to develop mathematical and kinetic models of the process, uh, because right now it is available only on a single phase in the process. It does not cover the multi parameter or multi process analysis. So hybrid conversion platform modeling is required, which is the most integrated design model to date. So development on this particular topic is also very very important. Implementation of an appropriate sorting process as well as source reduction of food waste, selection of conversion process based on the constituents of food waste, exploitation of a simulation model to maximize the food waste management system together with the conversion process parameters, and investment as well as the stakeholders combine efforts to improve the investment environment. These are the critical for ensuring the food waste valorization and the transition to the circular bioeconomy to accomplish this sustainably. Okay. If we compare in terms of the cost of fossil fuels, the prices of these products should be competitive, as we have seen that high production cost is first challenge which is there. So at present, about 85 to 90% of the output of petroleum refineries employed to develop fuels, while only 10 to 15% is the uh, through this organic sector production of organic materials. So here we have a very good opportunity because lot of biomaterials we can derive from this. So waste streams valorization, multi-feedstock biorefineries, new ways for biomass upgrading, all together with a complete life cycle analysis and sustainability index, we can establish this circular bioeconomy. So I complete this with the acknowledgement of my research colleagues, my PhD scholars, my institute and my department at SVNIT Surat. I also acknowledge the funding from various funding agencies from CSIR, Science and Engineering Research Board, Department of Science and Technology, and Gujarat Energy Development Association, and my family, friends, and Almighty to help me to implement this particular task. So, thank you very much, all the participants, for the patient hearing. And with this, go ahead with this 3 4 terms of reduce, reuse, recycle, remake, ultimately to establish this circular bioeconomy. Thank you very much. So, any questions?
Any questions from participants? One question is here, ma'am.
Yes.
Slide number 49. I'm visible, ma'am.
Yes, I
Hello.
can. Yes, slide number 49. Yes.
Hello. Slide number 49.
49, you said.
9. Film 4
Hmm.
shows higher hydrophobicity, while
Hmm.
the same film had the highest water absorption capacity at 65%.
Hmm.
Could you elaborate further on these two parameters?
Yes. So, through the contact angle measurement, see if your contact angle is higher than 90 degree, it means your material is hydrophobic. Okay, so that is what we have received this higher than the 90 degree. So, it is a hydrophobic material. At the same time, there is a water absorption capacity, yes, because though it is a hydrophobic, it is not super hydrophobic. So some amount of water absorption still will be there. So what would be the amount of water absorption? Because we have to this material, that product which we film, requires some amount of moisture. Okay, so if that moisture is not available, then also that product will not last long. Okay, so some moisture is required. So for that, that combination of water absorption and hydrophobicity, both is required for a typical type of application.
Okay, thank you. Uh, One more question is there.
Yeah.
Uh, Normally, black liquid from the pulp mill in the bagasse waste paper mill is burned for recovering the NaOH, so which also burn lignin.
Hmm. So we have to
Question is
see
in chat
the
box. Lignin already mentioned in chat box.
so
Uh,
chat box. Can you please repeat? Okay, let me see the chat box.
uh, Question in, please write
Yeah.
the question in chat box.
Is there a way to recover both lignin and caustic?
And
Okay.
one
So
other.
as I said, we have to identify the composition, okay, in which state, which form it is there, okay, because we do not know right now what is the percentage of caustic. So if it is only 2 or 8% of caustic, then the recovery cost will be very very high. It can be recovered because technologically it is possible, but cost will be very very high. So we have to perform the analysis that what is the composition, in which form it is available, which type of recovery method we can employ, and what would be the cost of that recovery, whether it is technically feasible, one thing, and another one is the economical feasibility. So both feasibility we have to check, and then only we can say that whether it is possible or not.
Okay. And one more question is there, ma'am. Uh,
Yes.
what are your thoughts on the which specific food waste hold the most promises for the commercial applications and product development in near future? Question is right in chat box.
See, actually, you have to study the literature, because people are now trying. See, conventional method is people are utilizing it for the extraction of some base materials like this. Either if it is oil containing, then extraction of oil, and then they throw it away just as a bio waste, or they produce the char. Okay, so not efficient utilization of all the components. Okay, so once again, uh, what it contains, what amount of carbohydrates are present, what amount of lignin is present, because every waste has a different composition. So which composition you can fractionate it properly. Okay, once again, the cost, which method you employ, you have to optimize the parameters, because each has its own parameter effect. So one has to study the technical details of all those food waste which has been published in open literature, because for a single waste we cannot tell that this is the best one, because for each, like I have given you the potato peel waste. Similarly, say we are working on the pineapple peel waste. Okay, so if it is a higher lignin containing, then if you produce the energy in terms of biochar and other polymers or biomaterials from other components, okay, how good recovery is after the fractionation. So technically feasible, but commercially or economically, how much feasible it is. So it is very difficult to say at this particular stage that this particular waste will be very promising. You have to identify whether it is a higher lignin based, then yes, for energy, or lignin based the biomaterials would be attractive. If it is a lower lignin, then yes, cellulose and hemicellulose, because here we have shown majority of the cellulose part, but we are also working on the hemicellulose. So you can develop or extract sugars and convert them in various biomaterials. Okay, so if those products are quite value added in terms of cost, then yes, it is attractive in terms of techno-economic feasibility. So to say one particular product is very very difficult, but yes, amount of that particular, like pineapple peel waste, pineapple crown leaves, a lot of amount of that as a waste material, 50% of 25 to 35% minimum as a waste is available. So high volume waste generation, but you see this food waste, they contain lot of amount of moisture. Okay, so how much amount of moisture, because to dry that, once again you require the energy. Okay, so we have to compare in detail.
Is there any way to recover both lignin and caustics?
Yeah, that I have answered already.
One more question is, ma'am, there.
Yes.
Please elaborate the concept of contact angle and their relation with water absorption.
I think first question I have answered. This was the first question I have answered. So I would say a lot of research and development opportunities exist if someone wants to work in this particular area, because afterwards also for your postdoctoral work or for the industries also, people are required with this type of knowledge. So I would suggest that if you are looking for some good work, you can have this area to look into. So Chandrapal, any other question?
One more is question there, ma'am. Can you please suggest DST, DBT, ANRF program that fund research in this area?
See, ANRF, you have to visit their websites regularly. DBT normally uh, focuses on the biological processes. So if bioconversion is there, then yes, DBT funds a lot of, there are various schemes you can refer to, and you can apply for the projects. SCRB, NRF, they are into the fundamental research as well as the applied research. So there they do not exactly, majority is not the theme based, but now after becoming ANRF, they are coming up with the theme based processes also. So you have to look into that themes, and if it is matches with your requirement, then you can apply. But yes, fundamental and applied research in terms of like chemical sciences or engineering sciences, and other engineering sciences also, materials sciences are there, or chemical engineering sciences are there. So when those calls are open, you can apply.
Any more questions from participants? Please write down on chat box.
No, there is no
Okay,
one
there
chat
is
box.
no. So here we have to take one photograph with all participants. So uh, please put on the camera on. Okay, मतलब presentation mode. Okay. Okay. Ma'am, please, can you please stop your screen sharing? Then you can take the photographs.
Okay.
इसमें वो आप कर सकते हो अपने से? हाँ, मैं Uh, please, all participants, please keep on camera on. Okay, ma'am. Thank you. Thank you very much, ma'am, for this informative sessions for our participants and giving you the valuable time for us.
Thank you.
So
Thank you
this
for
session was
inviting
very
me as well.
interactive and for giving the research opportunity for our participants to where which we have to apply and this all these things. So thank you so much, ma'am.
Okay. Thank you. So
Okay,
I
ma'am.
shall I leave now?
Yes, yes, sure.
Okay. Thank you.
Thank
Thank you
you.
once again.
Thank you so much.